everyone. Now we are entering in 8th session of the FDP. We are with a great personality, Professor C.K. Jaggi sir. Jaggi is professor and former head, Department of Operational Research, University of Delhi. He is recipient Shiksha Ratan Samman by Rotary Club of Delhi Uptown in September 2021. He has received the Amity Academic Excellence Award in February 2019 by Amity University Noida and Lifetime Achievement Award by International Organization of Scientific Research and Development Visakhapatnam, July 2018. He was honored with International Best Researcher Award 2017 by the International Science Community Association in the 7th International Science Congress at Bhutan. Certificate of Excellence Bharat Vikas Award was awarded for loyalty, diligence and outstanding performance in the field of operational research by the Institute of Self-Reliance Bhubaneswar in 2017. Besides these honors, he was awarded by various academic and research societies in India and abroad. He was invited to deliver Professor J.N. Kapoor Memorial Lecture at 20th Annual Conference of Vijnana Parishad of India at Manipal University, Jaipur 2017. His research interest lies in the field of supply chain and inventory management. He has enriched research experience with around 150 publications in journals of high repute. He has supervised 17 PhD and 26 MPhil. He is a life member of various learned societies. With that, I welcome again Professor C.K. Jaggi, sir, on the board. Welcome, sir.
Slides here, beta.
Thank you.
Professor C.K. Jaggi.
Yes, please. Can you hear me? Hello?
Welcome, sir.
Can you hear me?
Yes, sir.
Yeah, you are audible, sir.
Yes, you
Thank
are
you.
audible, sir.
Thank you.
Over
so
to you,
much.
sir.
Should I start now?
Yes, sir.
First of all, I would like to thank Professor Rajeev Kumar and his team for arranging one after the another wonderful programs. And
Thank you, sir.
today's one is also one of the feather in his cap. I really appreciate his working and team spirit, which he can take along not only his own department, but he can carry over so many people with him. Really, it is a pleasure to be associated with Professor Rajeev. Thank you.
आजकल में युवा पर वो रिसर्च प्रपोजल दे दिखाना है.
I'm just going to start. Can you see my screen? Is my screen
My
visible?
request to all the participants, kindly keep your video on during the sessions. And Professor Jaggi, I also request you keep video on yourself so that the participant can have a real feeling of sessions.
Just switch it on because I don't think whether it will work or not. Just see.
Thank you so much, sir. Thank you. You may start, please.
I was listening to the previous one. That was a wonderful thing he was talking about. But my topic is going to be a little bit different from it. We are just going to look into exploring the effect of lead time on stochastic inventory systems, basically. Is my PPT will work on the slideshow? Is my screen is still visible?
It is visible, sir.
It's moving
Quite good.
now? It's
Yeah,
moving?
exactly. Moving,
Okay.
moving, sir.
Okay. Thank you. Thank you. Yeah, just I just said because exploring the effect of lead time on stochastic inventory model. Just we want to mention here anyone who considers arithmetic method of producing random digit is of course in a state of sin. This was stated by a John van Neumann quote in conic section by D. McHall. Now, this is the overview. We just try to look into that. Now, this talk basically is going to discuss the stochastic inventory model for controllable lead time under various situations. For example, the controllable setup cost, backorder discount, uncertain supply, mutual coordination between vendor and buyer, service level constraint, etc. As we know that the increased competition, technological advancement, and the superiority of the consumer needs have led to the revolution of competitive paradigm in the area of inventory management. Therefore, certain inherent assumptions like deterministic demand, negligible lead time, etc., are need to be relaxed to improve the flexibility and usefulness of inventory models. Now, the utilization of JIT stands for just in time, includes low stock, shortening of lead time, and the setup cost, high quality, improved service, etc. The main purpose is the best possible use of available resources and reduce the process time as far as possible. Now, the companies like Toyota, Ford, Dell, Harley, Davidson, Motor Company, etc., are currently utilizing JIT. Now, the phenomena of crashing the lead time is applicable to the products like automobiles, electronics, computer accessories, etc. And these are the companies which are using this JIT technology. Now, inventory model can be broadly categorized as a deterministic and a stochastic. In deterministic model, it is assumed that the demand rate is known with certainty. In stochastic models, the demand or lead time or both follows a known or unknown probability distribution. When the actual demand exceeds the expected demand, or when the actual lead time exceeds the expected lead time, then one has to maintain the safety stock as a cushion against the uncertainties of the supply and the demand. Safety stock is directly proportional to the level of service being offered, higher or lower. The level of service, higher or lower, is the safety stock, but they are linked. If we are going to offer a higher level of service, naturally we are going to have a higher safety stock. Now, the service level indicates the ability of a firm to meet the customer's demand from the stock. It may be specified as a percentage of the total demand or the demand filled on time, that is within the specified time period after the receipt of the customer's order. In case the organization runs out of stock for an item which is in demand, it leads to loss of business and has an associated cost called shortages or the stock out cost. Now, shortage cost includes the loss of potential profit to the sales of the demanded unit, loss of permanent customers, goodwill loss, and loss in profit from the future sales. So these are very, very serious if we are having stockouts in our planning. Now, to minimize shortages, safety stock is generally carried out. In this context, the JIT philosophy is emphasized on a successful execution of all manufacturing activities required to produce the product and its fast delivery for the end user. JIT helps in continuous improvement in the manufacturing processes and in the elimination of waste, which ultimately helps the companies to provide better product and better service at a lesser cost. The utilization of JIT includes low stock, shortening of lead time and the setup cost, high quality, improved service. The main purpose is the best possible use of available resources and to reduce the process time as far as possible. Now let us see, say lead time plays an important role in a stochastic inventory system. The time between ordering a replenishment of an item and actually receiving the item into the inventory is referred to as lead time. The pre-assumptions is most of the authors have assumed that lead time as constant, fixed, or negligible, where it has been realized that lead time can be reduced by decomposing it into several components to make the system more efficient. So we can say the lead time is controllable and can be reduced by crashing it, its component, at an of course extra added cost known as your crashing cost. Components of the lead time. The lead time may consist of many components. For example, order preparation, order transit, supplier's lead time, delivery lead time, and setup lead time. These are all components of the lead time. I stated few, there could be more also that we can look into. Now, we try to look into a model that is a deterministic model specified by a set of equations that describes exactly how the system will evolve over time. Now, inventory, here just we see inventory level might be depleted at a slower or a faster rate during lead time. This is what we are trying to show it here. When demand is uncertain, safety stock is added as a hedge against the stockouts. The focus must be on the demand distribution during the lead time. And that is where the ROP is there, reorder point. And this could be one situation, this could be another situation, and this could be another situation. Because of the uncertainty, either of the situation can occur in practical situations. That is where we talk about the safety stock. Now, the reorder point and the safety stock. Now, reorder point R is defined as the expected demand during lead time plus the safety stock. And that is R, DL, that is the expected demand during lead time. And A sigma under root L, that is the lead time. Here A is a safety factor, we are saying. Sigma is your standard deviation of the demand during lead time. The safety stock and the service level, what we would like to talk. Safety stock determines the chance of the stock out during lead time. The components of this chance is called your service level. Service level is defined as the probability of not incurring a stock out during any one lead time. That is where the service level we talk about. The higher the probability inventory will be on hand, the more likely customer demand will be met. Now, if I say The service level 90% means that 0.9 is the probability that demand will be met during lead time, and 10% there is a chance of a stock out. There could be 4 different cases which we could look into. The first may be a demand rate is constant and lead time is constant. Second, maybe a demand rate is variable, lead time is constant. Or your demand is constant or variable lead time, or when both are variable. These are all 4 possible cases can occur. Now, the first case, if you look into the constant demand rate and the constant lead time, this is a very simple, as everything is known with certainty because both are constant. So that is why we can try to calculate this as a safety factor, and R will be given as this. This is the simplest one we can get easily. Now, when your demand is variable and lead time is constant, then the ROP, that is expected demand during lead time plus the safety stock, is defined as this. It is being replaced with your average demand, that is D bar, and that is basically your standard deviation of the demand during lead time. That is, and Z is your service level. Z and A, they are basically, it is a standard normal variate. Basically. Now, when the constant demand and the variable lead time, then we get this type of situation. Here it will be D, not D bar. That's a little correction. It will be D, not D bar. Because demand rate is constant, so it will be D. When both are variable, then this becomes the reorder point, the expected demand during lead time, and this is the safety stock, which is Z time, the standard deviation or demand during lead time. These are the simple calculation which we could find, and you just see one example of the same of case 4 when demand follows a normal distribution with the given data like this, or the having mean of 150 bottles per day and the variance of 8 bottles per day, and lead time is normally distributed with mean 6 days and the standard deviation of 1.5 days. Lead time is also we are assuming to be a normally distributed with this following information. Now the reorder point, if we are trying to calculate a 90% level of service, and then it is D bar, this is average we have taken, this is standard deviation, this is variance of the demand, which is given 8 bottles, this is average lead time, and this is standard deviation, which is given of the lead time, and 90% level of service, the value of Z is 1.28. And after substituting this, we can get this as my safety stock, and this is my ROP. If any one is a constant, then accordingly we can modify and we can get the other things also. Now, you just try to look into model, that is a periodic inventory model with controllable lead time and the setup cost with backorder discount. Now, this model basically discusses the effect of controlling the lead time and the setup cost in periodic inventory model with the backorder discount, where backorder discount has been considered as one of the decision variable. Now, when the unsatisfied demand occurs, a supplier offers the price discount to the customer for the stockout items to secure more and more backorders. Because his motive is to retain as many customers as is possible, because if he loses customer, then it is going to affect his business, because the goodwill loss, which cannot be quantified. The profit you can, but the goodwill loss that spreads with the word of mouth, that is very dangerous for any kind of a business. These are certain notations or which we use in the modeling. That is where the production level interview has the PDF effects with the mean of this and the standard deviation of this. These are certain assumptions which we have in this model, that length of the lead time does not exceed an inventory cycle, time so that there is never and more than one order outstanding in any cycle. That we are assuming here. The target level is defined as your expected demand during the protection interval plus the safety stock. Now, the lead time L can say has n mutually independent components, and the ith component has a minimum duration AI and the normal duration is BI, and the crashing cost CI per unit time. So what we do, we try to arrange this into an increasing order. That means C1 is a minimum and Cn is a maximum. Because why we are doing this? Because we are assuming this the least cost, because we start crashing with the minimum number of units and then we proceed on. So the lead time crashing cost per cycle can be calculated like this. Now we're trying to model it out. The consider a periodic review inventory model in which the protection interval X follows a normal distribution with PDF FX with the mean T into T plus L, where T is the cycle length and L is your lead time and standard deviation is this. Now, when we shortages have, when we have exceeding the stock, that means when your demand exceeds the stock, then this situation occurs. Now the expected inventory level at the beginning, and that we can calculate it like this. This is your total and this is my expected demand, and that is because shortage. The expected net inventory at the end of the cycle is like this. So the expected holding cost per period is calculated like this. We're just taking the average and then we are trying to run. The expected stock out cost per cycle is calculated like this. The two important concepts used in this modeling are backorder discount and reduction in the setup cost. Now, backorder discount is basically most of the inventory system consider the stockouts are partially backlog and partially lost. As some of the customers whose needs are not crucial at that time can wait for their demand to be satisfied, while others fulfill their demand from other sources. The cost of lost sale includes the profit loss and the unspecified loss of goodwill. During shortages, certain factors like well-framed product, fashionable goods, a certain brand, hi-fi equipment, cosmetics, etc., affects customers' acceptance for the back order. Suppliers' price discount is one of the major factors that motivates the customer to go for back order and help them to secure more back order through negotiation. This also facilitates the supplier to cut down the present and the future profit loss. Obviously, if you are able to retain more and more customers, that will be saved. Now we talk about this back order discount. This is assumed that a fraction beta, which is lying between 0 and 1, of the demand during stockout period can be back ordered so that the remaining 1 minus beta is lost. And the back order ratio beta is a variable and is a proportion to the price discount pi x offered by the supplier per unit, and that we take it like this. But this is lying between there, and that is pi x is less than your pi naught. Now we look into the reduction in the setup cost. Various components such as workers training, procedural changes, and a specified specialized equipment facilitate to reduce the setup cost, which not only eventually help the firm to reduce the total cost in the long run, but also improve the working of the present inventory. Now, as we have done it in the reduction of the lead time, similarly, we are trying to look into the setup cost also. Therefore, the setup cost K is assumed to be consisting of M mutually independent components. The jth component has a normal cost EI and the minimum cost DI, and of course the crashing cost is FI. When the normal cost reduces to the minimum, so there is a discontinuous relationship between the crashing and the cost and the setup cost reduction. We have arranged Fi in a similar way, F1, F2, Fn. Fn is the maximum and F1 is the least for the sake of convenience. Since it is clear that the reduction of the setup cost should be first on the component first because it has the minimum unit crashing cost, and then component 2 and so on. Also, the setup crashing cost per cycle is given by. Now, we try to model it. Our objective is to find the optimum value of the review period, lead time, and the backorder discount in order to minimize the total expected annual cost, which is given by your ordering cost and the setup crash. This stuff cost is
हाँ तो
calculated
बोलने
where this is given by this and psi A, which is phi A minus this, where phi and this are the PDF and the CDF of the standard normal distribution, standard normal value. That is what you are doing it in case of the normal distribution. That is, we get converted the whole expression which we had earlier, that is this one, under the, when we are assuming it to be a normal distribution, that looks like this. Now in case 2, when we do not know the distribution, but we know its mean and variance. So what we try to do, we try to play with this mean and variance of the data. The minimax approach has been used where the expected stockout costs are defined like this now, and the total expected cost is this. Now, using the necessary condition for optimality, we are just trying to take the derivatives with respect to t, phi x, and l. These are my decision variables. The replenishment cycle, lead time, backorder discount, and the total expected cost could be obtained for each component of lead time and the setup. Now, the nature of this function has been checked for concavity and the convexity by using the sufficient condition used for the second order that we have taken. That was the first model where we have done. In the second model, what we do is, there we have considered a stochastic inventory model with backorder discount and uncertain supply. Here we having supply is uncertain. Now, above given concept, crashing of lead time, setup cost, and backordering have been applied to a continuous inventory model, where the effect of uncertain supply has also been considered, adding to the same. There are many reasons for supply uncertainty, namely your shortages in the raw material, unpredicted machine breakdown, strikes. This affects the buyer's decision related to the safety stock, order quantity, lead time, and all. Here we add one more, that order quantity is Q, reorder point is R. Now F by Q is, and Y is a random variable representing the quantity received. The expected value of Y given Q, the probability density function Y that given Q are ordered. Capital X is what we take it as the lead time demand during demand, which has a mean of DL and a standard deviation of them. And theta is your bias factor, and T is your expected line, expected length of the replenishment. Now, this model involves the continuous review of the inventory, and the replenishment is made whenever the inventory level falls to the reorder point. It is assumed that the received quantity is a random variable which depends upon the quantity ordered. That means we are ordering Q, what we are receiving is. So the expected receiving quantity is going to be like this. That is where the bias factor is coming out to be. The expected amount received is a fraction of the whatever was ordered. That means because of this theta, which we are multiplying with the Q, so we are getting less. The variance of the received quantity is calculated like this. Now, in a similar fashion as we did in the previous model, we are assuming the partially backlog and partially loss. The expected shortage at the end of the cycle is defined as this, and the length of the expected cycle is this. Expected Y, that is theta Q by D, because we are not getting Q as we have ordered. The expected number of back orders, that is beta time this, and the annual expected cost function consists of the following: ordering cost, holding cost, stockout cost, and lead time creation cost, and that is where we can get this as a function of P of Y, R, and L. Now the expected cost function, which we have got this, we are substituting all the values and we try to get this as a function, that is objective function, the expected annual cost. Again, we have considered the two cases. In most of the models, we have considered the two cases, the normal and the known distribution, which is normal, and unknown distribution, where we use at times the minimax, or at times we use Chebyshev inequality. Upper bound of the expected shortages during lead time at the end of the cycle, when we consider the case first, that we get like this, as we have already defined. These are PDF and the CDF of the normal variation. Here, the necessary condition for obtaining the value of the order quantity and the back order discount, which minimizes, which we try to take the derivative with respect to and pi x, and Q we get this, and pi we get this. On the similar lines, we obtain the results of the case B, where it is unknown distribution, and we are using the minimax approach, that is distribution free, and we are playing with your mean and variance, and then the expected cost, annual cost, is defined as this. For case B, if we calculate, we get Q as this and pi x as this. In the third model, the stochastic inventory model with the service level constraint. Now we are adding something as a service level constraint here. Inventory problem with the controllable lead time and the shortages usually include the stock out term, which is difficult to determine in practice, as it consists of intangible components such as loss of goodwill, loss of profit, external shortages, and potential delay of the other parts of the inventory system. That is an internal shortage. When you are producing something and if you do not have the product which you require produce that unit, that considered as an internal shortage. And external is naturally when you are not able to fulfill the demand by the customer. A service level constraint implies that the stock out level per cycle is bounded. There, what we are trying to look into, putting the service level constraint. These are my assumptions. In the proportional demand and not met, stock out like this, safety factor, and that is what we are trying to look into, and try to look into how best we can do with the help of this. Now, the length of lead time does not exceed an inventory cycle, which we have already assumed in the initial stages. The target level R is expected demand during correction interval and the safety stock, and that we define it as like this, where A is again a safety factor and depends upon the service level 1 minus alpha, that where we are trying to put it. The inventory level is reviewed every T time units of time. Sufficient quantity is ordered up to target level R, and the order quantity is arrived after L units of time, which is a lead time. And we are assuming, as mentioned earlier, L is less than T. One order is outstanding in any cycle. Lead time thus consists of so many factors that we already explained. Now here we assume that service level constraint instead of stock out cost term in the total cost function, as it is difficult to compute the stock out cost in any inventory. The reason I have already said what are the reasons for not able to estimate correctly. This model examines the effect of reduction of setup cost and lead time in a periodic review model under the service level constraint, where the demand during the protection is assumed to be normally distributed and the proportion of demand that are not met from the stock is defined as alpha, and therefore the service level will be 1 minus, and alpha of course lying between 0. The total expected annual cost is again a sum of your setup cost, holding cost, lead time caching cost, setup cost, and subjective service level constraint. Now we will be making it a constraint optimization problem. Now, since this is a concave function of the lead time, therefore the minimum total expected annual cost will occur at the endpoint of the interval this. That is your Li and L minus. Moreover, the expected cost function is convex with respect to the review period and the setup cost. The necessary conditions for finding a solution is like this. We try to get the sufficient condition of the optimality has been used to see the nature of the total expected cost function. And of course, we try to do some sensitivity of alpha. So next, we try to look into your stochastic integrated vendor buyer model with a specific objective. So in this model, vendor aim is to reduce his setup cost as far as possible, and not only to compete in the market but also provide a better service to customers. This can be achieved by workers training, procedural changes, production, or installation of the new technologies, of course, at an extra investment. The buyer objective is shortening of his fulfill the customer's demand on time to maintain his reputation in the market. So here what we see, vendor and buyer both are having a different objectives. The vendor trying to reduce the setup cost, whereas the buyer trying to reduce lead time. These are again the notations as we already said, and there might be some more, that HP is the vendor's holding cost and HB is for the buyer's holding cost. Your buyer's ordering cost and this is vendor's ordering cost, and the rest all are parameters like the fraction of demand during the stock out beta, which is again lying between 0 and 1. Now, the product is manufactured with a finite production rate P, and P is greater than D. D is your inventory is continuously reviewed, and the buyer places the order whenever the inventory level falls to reorder point small r. The reorder point R is again defined as the same way, the expected demand during lead time plus the safety stock, that we take it as this, and A is your safety factor. Whereas the setup cost for the vendor, again we consider it has got an M mutually independent component, and accordingly we try to arrange it the increasing order of their crashing costs. Let the vendor be not be like this, be the total normal setup cost without crashing, and KVJ be the reduced setup cost when the jth component is crashed to their minimum cost, where J is 1 to M, and that we calculate it like this. That we are calculating the setup cost for the vendor when we are crashing it. Now, the total expected cost, annual cost for the buyer consists of ordering cost and the unit holding cost, stockout cost, and the lead time crashing. So he is trying to crash his lead time. That's what we try to write it as. Now the vendor's average inventory is the difference of the vendor's accumulated inventory and the buyer's accumulated. Hence the average inventory for the vendor can be calculated. Now we try to model down the total expected annual cost function for vendor includes the setup cost, inventory holding cost, the crashing of the setup. That is what it says. Now our target is to minimize the joint total expected cost per year for the vendor as well as the buyer. So we are adding these two costs and we get this as a joint total expected cost of vendor as well as buyer. Now again we consider the two cases where the unknown demand and known demand. Known we assume it to be normal, and unknown is unknown, and we try to use it as a distribution free analysis. We can use the necessary and sufficient condition to obtain the optimum solution, as well as check the nature of the joint expected cost function, buyer's order quantity and lead time, vendor's number of shipments, and cost. Now let us look into a small example and try to see what is happening here. So we are using this data D 600 units per year, KV for the buyer, KV is for setup for the vendor, HB is the holding cost, HV for the buyer, and HV is for the vendor, and the pi is your stock out cost, which are backlogged, and pi naught is loss. And sigma is standard deviation, that is 7 units, and P is 30. Production is 3200 units per year. Now we have lead time data and setup data. We are taking three components here. Lead time components 1, 2, 3. The normal duration is given, the minimum duration is given, the unit creation cost is also per day. Similarly, we have got the data for setup cost. Again, we are considering three: the normal cost, minimum cost, and we have a crashing cost, total crashing cost as reduced to minimum, that is also. Now for optimum solution, if we take beta 0.5 without crashing for normally distributed demand, we get this kind. Now optimum solution for beta 0.5 with crashing the lead time as well as a setup cost, which we are assuming to be normal distributed, and then we get the jointly when we are optimizing, we get this. That means total is this, and that is for vendor and this is for buyer. Just see what is happening here. When we do not have without crashing, we get this 936 for vendor. When we are having crashing of return, then it reduces to your 807, although the total cost also gets reduced to 4658, and the quantity is also reduced. We are having like now optimum solution beta without normally distributed is when this is for unknown distribution. Now just see we get this. We are here we have 4658 when we are having a normally distributed, and here we get 4963 where we are approximately arriving at the almost at the similar level, and that is the level which we are doing the crashing for the IF components, and then accordingly just try to obtain this. Now here we just trying to summarize all these results with the normally distributed, without crashing and with crashing, these are results which we get, and we try to look into the vendor savings or the buyer savings accordingly. And here is when you are having an unknown distribution, there also we get this, the total savings are almost close to what we get in the known distribution as well. Now, what we can observe here is that it has been observed that the crashing or lead time on the buyer side and the reduction of setup cost on the vendor side brings significant savings for the joint total expected cost. The expected cost for both the members reduces with the employment of the JIT technology, whereas the buyer generates more benefits as compared to the vendor. It is also observed that the joint expected cost decreases as the backorder ratio increases. Since the buyer can fetch a large number of backorders by reducing. It is also interesting to find that the crashing of lead time and the setup cost brings significant saving, approx 20 to 30% in the joint expected cost. The buyer saving is 25 to 28%, whereas for vendor it is 8 to 10%. Now, so far we are assuming the units are non-deteriorating, non-decaying units. That means whatever the units we have, we can store it for as long as these two. Now we try to develop this model, of course, with the controllable lead time under backorder discount, decaying product. Now the main objective of this model is to uncover the benefit associated with the reduction of lead time and offering backorder discount for decaying products under the service level. Again, we will be considering the two cases for demand known, demand distribution is or demand distribution. We try to use Minimax for finding the solution to find a solution. And here we have all the data like the stations and the similar what we have already used in our. Here we have the class of PDF in all this, fix what is cost, and the proportion of the demand that are not met accordingly. That theta is a constant decay rate. That is time to follow iteration is a negative exponential. And when we are trying to find out the rate, we use the hazard rate function from the reliability. That means PDF upon 1 minus CDF, and that gives me the rate as theta as a constant. And when we theta comes, when we having time to follow iteration is negative exponential. Verify that is goes like the same way. So here we assume that the item decay with a constant rate per unit of on-hand inventory, the quantity or the decay is considered consumed, and thus this decay is like a source of consumption. That you cannot play because that says there is no replacement or repair of a decayed unit given cycle. That goes as loss basically. Holding cost will be charged on the actual inventory on hand and does not include the inventory level is reviewed after every T units of time. A sufficient quantity which is ordered to bring level back to R, and the order quantity arrives after your L units of time, that is your after the lead. And the lead time L does not exceed that we are assuming, that means no one single order is outstanding any cycle. Now the target level again is defined as a similar way, that is the expected demand during the production interval and the expected decay during production interval. That terms is added now because that is we need to look into that, and the safety stock. That is where we get to know that. And where mu is the average number of units decaying per unit of time, and SS nothing but your A star, the standard production interval, and A is your safety. And that would get as X like that. Q represents the allowable stockouts probability during the cycle length and the lead time, which means the service level is defined during the protection interval. Again, we break down L into n mutually independent components, and we arrange in the increasing order of their crashing costs per unit, and that's the way we use it. Now here let L naught, which is like 1 to n Bj, with the length or lead time with the component 1 to I crashed their minimum duration, then can be expressed Li as L naught minus this, where I goes 1 to n. Time creation cost per cycle is given. Assuming that the fraction beta of the demand during stockout period can be backordered, so the remaining 1 minus beta is lost. And the backorder ratio is different. Here, our model is different from the previous model. That is, initially, this factor we are talking about, pan Hasio, that is 2000. And we are introducing again a service level constraint as we have already done in the previous model. Then we try to look into how this works. Expected net inventory at the beginning is this, and the expected net inventory at the end of the period is this. So the average, if we take out this becomes my average. The expected decay cost has been calculated like this. Expected stockout cost is calculated like this, where expected X minus R plus is the expected demand shortages at the end of the, or expected shortages at the end of the cycle. Then we try to formulate this model and try to calculate maximizing the expected cost, that is maximizing the order cost, stockout cost, holding cost, lead time creation cost, and the decay cost, and that is subject to the constraint. Also, we have assumed that the backorder ratio beta depends on the backorder price for the decaying product, and that we have taken as this, and R is like this, where A is your safety factor. The equation 1 can be rewritten as this. We are just simplifying the substituting the values, and that eventually get to this constraint. Again, we have, as I mentioned, there are two cases of normal distribution and unknown distribution. Now, lead time demand with the normal distribution, we get the expected shortages during end of the cycle like that. And the total function, the total cost function after substituting, and that becomes like this. And when lead time is unknown, and then we try to use the minimax approach, and that way this becomes like this. And our total expected cost, average cost is given like this. This is the least upper bound, that is what we are trying to find out. Lead time demand with unknown distribution, that it can be shown that CW, that a function, this is a convex with function for L belonging to this for a fixed time T and pi s. Before the minimizing the upper bound of the expected total annual cost will occur at the end of the lead time period for a fixed value of T and pi s. Moreover, it can be shown that this is a convex function with respect to, for fixed L with respect to T and pi x. Now, in the solution procedure, thus for the fixed L, the minimum value of this will occur at the point T and pi x that satisfies this condition. If this is 0, then we get this. And solution procedure is when we are solution procedure using your normal distribution. If that is 0 and then pi x we calculate like this. Since it is difficult to obtain a solution for t and pi x explicitly, as the evaluation of equation 4 is this. And equation 5 needs the value for each other. As a result, we must establish some algorithm which helps us to find out the value of t and pi x. And that is what we propose, the iterative solution algorithm. And following this algorithm, for a given allowable stockout probability, we can first find the value of safety factor by checking the standard normal table and thus obtain the value of xi a, and then we try to, for given value of a and xi a, for each li we try to use. Now for each pair of pi ti, pi xi and li, we compute the corresponding total expected annual cost, where this satisfies the service level constraint. That is check for this, that we need to verify it. Then we try to find out the total expected cost, where the service level constraint is satisfied. And that gives me the local optimum. Following this solution procedure, that is solution for minimax, that is what we try to do, this equation. Then again we follow some iterative procedure for minimax distribution. That means minimax solution, minimax approach. For any given q, we divide the interval as this into n equals subintervals. When n is large enough that a naught is equal to 0 and an is this, and subsequently your aj is nothing but aj plus 1, that is not equal, that is plus 1, and this. And accordingly, for each equation li, we try to calculate this from equation 18 and 19, and for each li, compute the corresponding values. Then we try to find out this, and we try to look into the service level constraint is satisfied. Then we try to find out that is becomes the optimum solution, and this is optimum. We try to look into an example of the same. Now to illustrate this, that we assume that demand is 600 units, your ordering cost, stock out cost, and your sigma, that means standard deviation, that is 7 units, y naught, and h, the ordering cost, q is 0, where a naught is 0, and an is 2, and n is 2. We have a all for different service levels, that means A 2.05 and A that is 2.33, that means this way. And these are all different level, service level, that is a value, and then we try to find out the value from the standard normal table, and that is by checking this table from the Silver and Peterson on these pages. You know, here. Now, lead time data we are taking as the three components. Normally, normal duration, then we have a minimum duration, and then we have a crashing cost. And that is lead time per week, that we, if we calculate this crashing, and that we get this like time data. Here, say the crashing or lead time when the protection interval demand is known for iteration rate is 2%. That means theta we are considering it 0.3 times is 0. And that's what we try to calculate. These are my factors. There's a lead time crashing, and these are my expected costs when we are having for normal distribution. Here we consider this for 99% level of service. There we had 98. Now we consider it 99% level of service. Now we consider 96. That means that we are just varying this level of service and then trying to calculate data for the normally distributed. That is for 80%. Now, we're just summarizing this all. 98, 99, and 96 and 80, and iteration rate we are keeping it constant as 2%. 2%, right? Here, what we see the expected cost which is coming. We'll calculate it. Just see here, when the 80% level of service is there, the cost is very high. When it is 99 as compared to this, that means very low, because we are able to retain that way. Now, you just see the optimum solution iteration rate of 5%. The same level, the iteration rate goes high. Again, that is going very high, because the stock out cost is going to play a vital role when we have a less level of service constraint. That means we are having only 80% of the level of service, then this like this. This is for 8%. If you are increasing now iteration rate and then doing all the calculation for all the service level, 98, 99, 96, and 80, and accordingly we are just trying to evaluate this. Now, for 2% when unknown distribution, that is now this cost comes up. 2% iteration rate, and that is unknown distribution. Similarly, we go for 5% also for unknown distribution, and then go for 8%. Now, what we try to observe? We observe that when we solve for different values of beta, beta 0 represents the complete one complete back order, and beta is lying between this. We have also observed that the total annual expected cost decreases as the back order ratio, because The natural phenomena is if the supplier can fetch as many customers back with help of backorder discount, that helps him to reduce his cost. The review period is the maximum and the maximum inventory level for decreases with the reduction of the. Naturally, when you have a less lead time, that means frequently you are ordering or receiving, then that means loss due to decay will be, because you are refreshing your stock frequently. That's what the philosophy of the deteriorating modeling is. Further, the total cost increases at the rate of decaying lead. Actually, when your decay rate goes up, the loss due to decay will be higher, and so as the cost will go higher. It is observed that the reducing the lead time and the expected cost decreases with the backorder ratio is positive. It is also observed that when the service level becomes low, the expected annual cost becomes high. Obvious. Service level low, naturally you are going to have more losses. I mean, the form of the loss sale that will go. Now, if we conclude the whole, the crashing of lead time is a very natural phenomena. Inventory. But in the literature of deteriorating items inventory model, there are very few search efforts which the effect of controlling lead time has been considered. While unsatisfied demand occurs, a supply offers a price discount to customers for the stock out item, secure more backorder. That is why we have considered the dependency of the stock out backorder ratio on account of the price discount. Usually in crashing one tries to reduce the time, which is crucial for deteriorating item, and to achieve this one requires additional resources which cost money. Therefore, one looks for a trade-off between the time and the cost. It has been shown that from the result that the review period T and the maximum inventory level of deteriorating item decreases with the reduction of the. That's what we can look for. Post models can not only provide greater flexibility to the inventory manager, coordinate his inventory in more efficient manner, but also makes numerous savings in the total cost. In fact, the initial investment for reducing setup cost seems to be higher, but eventually it reduces the total expected cost of running. Such kind of model facilitate the trade growth and satisfy the supplier's, buyer, and the consumer's requirement. Differences of models. I'll stop here.
Thank you, sir, for a nice talk. Any question from the participant? Yes. Any query? Okay, sir, I think there is no query. So let's thank the speaker. On the behalf of the organizing team, I would like to thank Professor C.K. Jaggi for giving his precious time to us. He talked about stochastic inventory models for controllable lead time for such as the conditions, controllable setup cost, backorder discount, uncertain supply, and also he told us about utilization of JIT in low stock and also shortening of lead time and setup cost. Also, he discussed about reorder level safety stocks. So, thank you so much, sir.
Thank you.
Sir, it was really a wonderful talk from. Sir, it was really a wonderful talk and very nice slides you have shared with us. I was really motivated to work in this area also. In fact, my work is on the reliability modeling and information theory. But going through this practicality of your models, I'm really impressed. Hopefully, the other participants who have joined over here having a research area, interest in this area, get motivated by your this wonderful talk, and you have very well explained about these models, sir. Thank you from all MDU fanatically for giving us a valuable time for this FDP, sir. And your blessings and motivation always encourage us to have more and more better for the department in the university. So nice, sir.
Sir, I would love to see you working in the same area.
Yeah, sure. So it will be nice time. Okay, in future also have such interactions with you, sir. And sorry, we are in the online mode. We cannot offer you the lunch right now. We like to have the lunch of yours with all participants. Hopefully, in futures to come, we can have such event also. So thank you all. And now you see we have the lunch time. So you enjoy your lunch, service for this lunch. So have a good day, sir. Thank you so much.
Thank you. Thank you so much for inviting me also. I should say. Thank you so much. Thank
So
you.
I request the participants be attentive regarding your attendance sheet. Always mark attendance in the sheets which is being provided to you or the chat box. Sometime a request is received from the participants sharing the request to share the sheets after the session is over. So my humble request to the participant is go through the chat box. We just already provide you and go on providing you this sheet prior to the end of the session. So you have to connect here only. Then you can have this sheet. We will not share you this thing in the WhatsApp or email. So it is your to ensure it that you join the session and also fill up your attendance sheet. This is essential from your part. So kindly take care, and I also request to participants kindly keep your video on so that it seems to be a live session from all sides, and we can have yes, interaction also. Now my request is to the participants who have joined over here, please on your video, and Professor Jaggi, you also, if you are there, kindly on your video so that we can have a beautiful pic along with you. So I request all the participants, please on your video, and to the Professor Jaggi also, please on your video so that we can have a beautiful pic with you of all the participants. Kindly, I once again request you all, please on the video. Screen share off करो. I could not see much videos. I don't know what the issue is. Kindly on. I request all the participants and Professor Jaggi to on your video so that we can visualize everything. Yes, you are visible, sir. Your video is okay. And I'm requesting the participant also so that we can see each other. Okay, Kajal, have a pic. Got it? Yes. Very few participant pic is there. Faces are visible. So, sir, you have a beautiful pic with us. We'll share with you also.
Thank you. Thank you, sir.
Thank you so much. Thanks a lot.
Thank you.
ये फोटो तो बहुत कम में किया है ऑन नहीं करते ना कैमरा
ऑन नहीं करते now it So we will meet at 2:30. Okay.
Lunch sheet भरने के लिए
Dear participants, also fill the attendance. Okay, the link is shared in the chat box. Please fill that. And it is humble request to all of you, please keep your camera on during the session. So now you can enjoy your lunch. Okay. So we will meet at 2:30.